So this is the last section of Chapter 7 that we'll be doing, 7.3, which is applications of linear programming. So we're going to be putting everything together that we've been doing in the previous sections. We're going to practice writing constraints as linear inequalities. And the linear inequalities that we're going to expect to see are greater than or equal to and less than or equal to. Generally, you don't come upon the strict inequalities when you're doing an actual business problem. Then we're going to graph the feasible region. So that's what we've been doing, where we've been finding the region that's enclosed by some lines. And then we're going to construct the objective function. The objective function is, what are you trying to optimize? And for us, it's frequently going to be profit, revenue, or cost, but it can be something else. Then we're going to do the whole solving a problem by using the graph of the feasible region and the objective function together to find the maximum and minimum values of that objective function. So remember that linear programming is a technique that helps businesses make decisions about how to use their resources, and any limitations on time or space or number of employees get taken into consideration to make an optimal decision. So we're looking at very simple scenarios here, but this can easily be expanded using computers to as many variables as you need. So this is our example of a linear programming problem that we've been looking at, and we're going to actually solve it in this section where we have chainsaws and wood chippers being assembled, and we want to maximize our profit. So the first step is to write any constraints that you have as linear inequalities. So we've been working on these. Linear inequalities have an x and a y, and when you draw the graph, it's a straight line. The first step to all these problems is always going to be to clearly define your variables. So here we have canoes, but we're going to have x equal the number of canoes because there's a lot of information you could be collecting about the canoes. What's their capacity? What's their weight? Their cost? We want to know how many of them. So you need to be very specific when you write your definition of your variable. So x is the number of canoes, and y is going to be the number of rowboats. So most of our problems will have 2 or at most 3 different items. So the canoes need 8 hours to put them together. So I'm finding it really useful with these problems to make a chart and put time as a column in the chart and collect that information here next to the canoes of that they need 8 hours to fabricate. And then by the rowboats, I would put that they need 5 hours to fabricate. So then I can see that if I want to know the total amount of time for labor, if I write 8x, and it's 8 hours for each canoe, and I multiply it by x, the number of canoes, then 8x is the total amount of time for canoes. And then I have 5y, I have 5 hours per rowboat times the number of rowboats, y. And then I need to add those together because I'm going to total them up. And this can be at most 110. So it can be 110, but we'd be even happier if it was less than 110. So this is writing a constraint as a linear inequality. Okay, so let's do another example. In this example, we have, again, 2 kinds of things. We have radio ads and TV ads. So I'm going to have x be the number of radio ads, and y be the number of TV ads. And again, I'm going to make a chart. And here we're looking at the cost of the ads. And radio ads are $250. TV ads are $750. So now start looking for patterns here, because if it's $250 for each ad, and we have X radio ads, then 250X gives you the total cost for all of the radio ads. $750 for each TV ad times Y, the number of TV ads, gives you the total amount of money spent on TV ads. And then we want the total of that to be no more than $9,500. So it can be equal to $9,500, but we'd be even happier if it was less than that. So that's the English no more than translates into less than or equal to. Okay, so do as many practice of those as you need. There's quite a few of them in your homework. So here's another example with chainsaws and wood chippers. So one more example where we have X equal the number of chainsaws and Y equals the number of wood chippers. And again, I'm going to make a table. And here we're talking about assembly time again. And the chainsaws need 4 hours, and the wood chippers need 6 hours. So hopefully you're starting to see the pattern that 4x plus 6y is the total amount of time it will take to put together all of those machines, and that has to be a maximum of 48. So maximum less than or equal to, no more than, all of those translate into the same inequality. Okay, then this example is a little different, so I picked this one so we would have an example of a slightly different one. So here we're mixing two kinds of coffee, deluxe coffee and regular coffee. And we want to make at least 50 pounds. So now we're talking about pounds of coffee. So X is going to be pounds of the first kind, the deluxe coffee. And Y is going to equal pounds of regular coffee. And again, I'm going to make a chart. But this is going to be a little different because we need them to make at least 50. So that's kind of a whole different thing. At least 50 total, the blended coffee. So X plus Y is the amount of blended coffee. Needs to be at least 50. So it needs to be 50 or more. And then it has to have at least 10 pounds of the deluxe. So X needs to be greater than or equal to 10. So this example is different. You have to read the words carefully. And let me recommend that you practice a technique called 3 reads, where you read the problem through 3 times, and each time you're looking for different things. The first time you're looking for, what is it that I'm working with? Coffee, 2 kinds of coffee. The next thing is, how is it being measured? Pounds of coffee, amount of hours of time, dollars, whatever it is. And then the third time, read for meaning and making sense of it and understanding the problem thoroughly. Okay, next step in solving these problems is to graph the feasible region. So for the last example, we said deluxe coffee is going to be mixed with regular coffee to make at least 50 pounds of a blended coffee. So we had X was pounds of the deluxe coffee, and Y was pounds of the regular coffee. Trying to see if I change the size, if my grid will look any better, but apparently not. Okay, so then we had X plus Y had to be greater than or equal to 50, and X had to be greater than or equal to 10. Okay, so I have big numbers here. So I'm going to think about how to make my graph so that I can show these big numbers. And I'm going to just make another grid down here since that one's not behaving properly. And I need to get up to at least 50. So I'm going to go 10, 20, 30, 40, 50. And as long as you show the reader of the graph what your boxes are standing for, You can have the scale be whatever you like for convenience. So pick nice numbers to work with. So the first inequality is that x plus y is greater than or equal to 50. So we need to draw the line x plus y equals 50. And here is where the intercept method really comes in handy, because when x is 0, y is 50, and when y is 0, x is 50. So my x and y intercepts are both 50, and I draw the line connecting them. Well, now I have to decide which side to shade. So if I test 0, 0, I'll have 0 plus 0. Is that bigger than 50? Nope. So I need to shade away from 0, 0. Okay, then the next line I need to graph is x equals 10. And this is a vertical line. And everywhere on this line, x equals 10. So this is the vertical line, x equals 10. And then if I want x values that are bigger than 10, I find those to the right. So I need to shade to the right. So you can see that my feasible region, oh, we need one more condition. We definitely don't want negative values of x or y. So we need x is greater than or equal to 0. Oh, that's included in x is bigger than 10. But we also need y is greater than or equal to 0, so that we only have actual conditions that can occur where we have positive numbers of pounds of coffee. So this shaded region is called the feasible region. Okay, so that's the instructions for this part, is just graph the feasible region. And then there'll be another step that we need that we'll continue on with this problem in a moment. So now we're going to work on the step of construct the objective function. So generally, these are going to be profit, revenue, or cost. Occasionally, it might be something different. So in this case, maximize profit is said in the problem. So the objective function is going to be a profit function. But we always use z equals for the objective function, whatever it's representing. It's always z. Okay, so we already started working on this problem where we had x was the number of chainsaws and y was the number of wood chippers. And then we made our chart and said the amount of time for a chainsaw was 4 and for a wood chipper was 6. Well, now we're given a little bit more information about profit. And it's $150 for a chainsaw and $220 for a chipper. So you can see that this chart just really helps us organize all of our information. So the inequalities we need was 4x plus 6y had to be less than or equal to 48, a maximum of 48. And then we're pretty much always going to need x is greater than or is equal to 0 and y is greater than or equal to 0. So don't forget those because they are important for making the feasible region correct. And then we need a profit function. So the profit function again is linear. It says the profit is going to be $150 for each chainsaw times the number of chainsaws we're representing with x, plus $220 for each wood chipper times the number of wood chippers, and we're using y for that. So this is construct the objective function needed to maximize the profit, and that's going to be the last step of our process. Okay, so let's look at this coffee example again, where we had X equals pounds of deluxe coffee and Y equaled pounds of regular coffee. Then we made our little chart. And this time we can't really use the chart very well for writing the inequalities, but we can collect our cost information here. So deluxe coffee costs $6 a pound and regular coffee costs $5 per pound. So construct the objective function means to write z equals, and z is now representing cost, but we always use z, $6 for each pound of deluxe times X pounds of deluxe, plus $5 for each pound of regular times Y pounds of regular. So this is construct the objective function to minimize the costs. And then that's going to be the last step of the process. So I'm going to pause here and make another video with the rest of this section that is completely solving the problems.